Welcome to the first of a 5-video series on algebra basics, integers. So what are integers? Well, let's start with the basic numbers we know, 1, 2, 3, 4, 5, 6, 7, and so on. These numbers are called the natural numbers, and you'll see them denoted by a double scripted n from time to time. Well, how about 0? Is 0 a, quote, natural number? Well, not by definition. If we consider all the numbers 0, 1, 2, 3, 4, and so on, we typically call those whole numbers. Now, what if we were to throw in the negative numbers as well? What would that whole group of numbers be called? Well, we refer to that set of numbers, all the positive and negative whole numbers, as integers, often denoted by a double scripted z, which comes from the German word Zahl for integer. And that's the basic sets of numbers and their names. So to summarize, here's your natural numbers. Throw in 0 to that set and you've got all the whole numbers. Throw in the negatives to that set and you've got all the integers. Now this first video is about how do we add, subtract, multiply, and divide integers. So let's begin with adding integers. Here's an example. Suppose we wanted to add 5 to the integer -3. Well, there's a rule that if you're adding opposite sign numbers that you subtract and you carry the sign of the larger number. Let me explain. Here we have a -3, and here we have a 5 without a sign in front of it. In mathematics, that means that the 5 is positive if no sign is indicated. And so because I'm adding opposite signs, a positive and a negative, I subtract them. When you subtract 5 and 3, you get 2. Now, the result carries the sign of the larger number. 5 is larger than 3, 5 is positive, therefore the result is positive. We don't often write +2 as the result because +2, or +2, is the same as 2. Here's another example. Here I'm adding a +4 to a -9. Again, opposite sign numbers. So I subtract. When you subtract 4 and 9, or 4 from 9, you get 5. But because the result is supposed to carry the sign of the larger number, and 9 is larger than 4, then the result is negative. Here's a third example to which the rule you see at the top of the screen does not apply, because here we're adding same sign numbers, or in this case, we're adding 2 negative numbers. When you add 2 negative numbers, you add, and the result is negative. 7 plus 2 is 9, so adding 2 negatives results in a -9 in this case. So those are the basic rules on how to add integers. There's a little bit more to say here. First of all, why? Why were these rules created the way they are? That's a long story, but it has to do with the numbers representing things that are happening in science and in actual real life. So the reasons why these rules were chosen is not really discussed here, but there's a long history and a background behind it, but that's worth noting. Here's another thing worth noting. If you're watching this video, you probably have had several math teachers in your past explain many different mental tricks to remember these rules. One that I like in particular is the notion of thinking of positive numbers as quantities that you have and negative numbers as quantities that you owe. So in this first problem, 5 plus -3, we can think about that as having 5 and owing 3, a result that would end up, if you paid off your, quote, debt, would end up with you having 2 left over, and hence the answer is 2. On the second problem in the middle, we can think of that as having 4 and owing 9, a result that would be owing 5 because we couldn't pay off our whole debt of 9, only part of it. And you could think of the answer as -5 that way. In the bottom problem, using the having and owing analogy, you could think of two negatives as two different quantities that you owe, so you owe a larger quantity. Now, I particularly like this analogy for adding positive and negative numbers. Chances are you've heard tons of them, and every teacher has a different story to go with this kind of situation. These stories that we tell, including the having and owing analogy that I just shared with you, these aren't real math. These are mental tricks to speed up the process for us and to sort of make something stick to our brain, so to speak. But if the having and owing doesn't work for you, there are many other ways to think about these. Ultimately, you have to figure out a trick on your own for how your brain is going to attach itself to these kinds of problems so that they become very quick and almost automatic in your mind. One last thing worth mentioning here, these problems are occasionally, in some websites or textbooks, written with parentheses. Take a minute to look back and forth. Now, I myself am not particularly fond of putting parentheses around the numbers like this, but I think it's a confusing notation. However, I just wanted to give you a heads up warning that if you're working on some website or in some book and you see parentheses around the numbers, it doesn't change any of the rules. It's just another way to write the problems. Again, one that I'm not particularly fond of. Let's take a look at subtracting integers. Subtraction in algebra means to add the opposite. I'll show you what I mean by that. Here's a problem. 8 minus 3. Well, I think we could all agree that 8 minus 3 is 5. Of course, the way we were taught this when we were young is that if you have 8 things and you take 3 of them away, that you have 5 left. Now, that's not wrong. But in algebra, we like to think of things a little differently. So when you see 8 minus 3, of course 5 should come to mind. But technically, what that means is to subtract 3 is to add the opposite of 3, or to add -3. Now, it may seem like a weird way to look at it, but that's the perspective in algebra. Now here I'm adding two opposite sign numbers, so I subtract them and I take the sign of the larger number, just as we saw in the prior problems. Now, am I suggesting that when you see 8 minus 3 in an algebra problem that you write it as 8 plus -3? No, that's a little bit overboard, but this does give you a general idea of the concept that subtraction is really the adding of a negative. Let's look at 4 minus 7. To do 4 minus 7 means to take 4 and add the opposite of 7, which is -7. Here, once again, I'm adding opposite sign numbers. And as we just saw in the recent problems, when you add opposite sign numbers, you subtract and take the sign of the bigger number, which in this case is 7. Here's another problem. -2 minus 8. To subtract 8 means to add the opposite of 8, or -8. But here, when adding two negatives, you actually add the numbers and the result is negative, just as we saw earlier. Here, I'm subtracting a -1. To subtract a -1 means to add the opposite of -1, in other words, to add 1. And now I'm adding opposite sign numbers, so I'll subtract and take the sign of the bigger number. Notice, by the way, a quick math shortcut, subtracting a negative is effectively the same as addition. Now, while those are the official rules, if you're watching this video, you're probably less experienced at these problems than me. I've been doing these problems since 1982, and I've had a lot of time to develop quick little shortcuts in my head, and ultimately you're going to have to do the same thing. Take a minute to look at these problems and see if you can connect the problems to the results in a way that's meaningful to you. I recommend, if this seems new to you, to pause the video and really spend some time just looking at this still and seeing if your brain can attach some kind of logic to it. Because even though I've explained all the rules as they officially are, when we're doing algebra problems, we often don't have time for the lengthy official rules. In other words, take the third problem on this slide, for example. You have to get to the point in algebra where when you see -2 minus 8, your brain instantly pops to -10 without going through a lot of cumbersome rules. Now, the rules are there to get us started, but I recommend that you pause the video and see if you can make some sense out of this in your own way, because that's ultimately how you're going to need to proceed. Now let's take a look at multiplying integers. Here's the basic rules for how to multiply an integer. So let's look at the first one, a -8 times a -5. Well, it turns out a negative times a negative is a positive. And of course, 8 times 5 is 40. So when you're multiplying integers, you kind of ignore the signs and just do the multiplication problem, and then determine the sign of your answer based on the two rules you see at the top of the screen. So 8 times 5 is 40, and since a negative times a negative is a positive, the result is positive 40, also known as just 40. So let's do this one. A -3 times 4. 3 times 4 is 12, but according to the rules, a negative times a positive is a negative. 2 times 7 is 14, but a positive times a negative is also a negative. Now, it's worth pausing here and asking, why are these rules the way they are? How did it come to be that humans decided that a negative times a negative would be a positive and a positive times a negative would be a negative? Where did all this come from? Well, that's a really interesting question and a very long story of how this developed over the centuries to be what it is. Ultimately, it's too lengthy of an answer to really go into it here, and it doesn't fit in well to this video, but it's worth noting that all of the strange rules you see in math, and I'm generalizing beyond just this one, all of them come from the desire to have mathematics represent something in science, engineering, and real life. Mathematicians certainly could have made a rule that a negative times a negative would be a negative. But rules like that would fail to represent some physical realities that we've encountered in the world, and so we tend to discard rules when they're not useful for scientific purposes. Okay, by the way, before moving on, it's worth reminding you that 0 times anything would be 0, of course, as our last example. It's also worth noting, before we move on to division, that sometimes instead of the dot that you see here to represent multiplication, you'll see the numbers next to each other with parentheses around one of them, or even both, and that this also represents the exact same multiplication problems. So let's take a look at dividing integers. The rules for division, turns out, are the same as the rules for multiplication. Here's a first example. So here we have a negative divided by a negative. First, let's ignore the negative signs. 20 divided by 5 is 4. Now, since a negative divided by a negative is a positive, the result is positive 4. In other words, just 4. Notice the division symbol in between the -20 and the -5. That is not a symbol that we use in algebra. So from now on, when we have a division problem, we'll write it as a fraction. This also means -20 divided by negative 5, which again is positive 4. So in that way, here's our next example. Ignore the negative sign for just a moment. 30 divided by 6 is 5. But because a negative divided by a positive is a negative, then the result is negative 5. Here's one more example. 12 divided by negative 6. 12 divided by 6 is 2, of course. And when you're dividing a positive and a negative, you get a negative. And now that we've covered division, let's look in more depth at a special case, division problems involving 0. Here's a division problem where 0 is in the denominator, or we're dividing by 0. Here's a division problem where 0 is in the numerator. And here's a division problem where both the numerator and the denominator are 0. Now, it might seem on first thought that any division problem involving 0 has an answer of 0, and I'm sure there were originally mathematicians who tried to argue this case. But it turns out some of these statements here, they decided against. And let's go through the logic on what they decided, historically speaking, and why. Before we do, let me remind you that division is essentially the reverse of multiplication, in the sense that 10 divided by 2 is 5 because 2 times 5 is 10. And that's not surprising to most of us, but let's try to apply that same logic to these three proposals. Suppose a mathematician were to say, all of these should have a result of 0 because division involving 0 has a result of 0. Well, it turns out not to be very logical, and here's why. Following that same pattern, let's look at the first one. If that were to be the case, then 0 times 0 would have to be 7. But of course that's not true. And so it was decided that a non-zero divided by a 0 shouldn't be 0. So what is it? We'll get to that later. Let's look at the second one. For 0 divided by 4, or 0 divided by a non-zero, to be 0, it would seem that following that same pattern, 4 times 0 would have to equal 0, which of course it does. And so mathematicians decided that 0 divided by any non-zero should be 0. Now let's take a look at the third one. 0 divided by 0 equals 0. Suppose that were the proposal, that we make that the result. Well, if we're going to make that the result, then 0 times 0 would have to be 0. And while that is true, and there does appear to be some logic to this, and I'm sure many mathematicians argued in favor that 0 divided by 0 should be 0, there had to have been others that said, well, wait a minute. What if we claimed something ridiculous, like 0 divided by 0 equals 5, or just any number? That also fits the pattern. 0 times 5 also equals 0. So it was decided that 0 divided by 0 shouldn't be 0, or anything else for that matter. Ultimately, if you got a little lost in the logic, the good news is all you really need are the final results. Here's the final results of decades of arguing among mathematicians. In the top line here, 0 divided by any non-zero number is 0, but looking at the bottom two divisions, any division where 0 is in the denominator, it was decided wouldn't be a valid division problem. The phrases that have come up over the years are many. The two that have stuck are that this division problem or this fraction is undefined or it doesn't exist. Essentially, when we're dividing by 0, we think of it as a non-answer. And that completes the first of 5 lessons on the algebra basics.